In section 3.2, we're going to take those determinants that we calculated and we're going to look at some properties of determinants that are going to be pretty, well, they're very important determinants and they're going to connect us to the stuff we did in chapter 2. So the first thing we're going to look at is just to calculate some determinants that we've done before that we see. So we have this matrix here. This looks like the identity matrix with a -3 in row 1, column 3. So this is obviously triangular. So notice that the determinant can be calculated by taking the diagonal entries multiplied together. And so the determinant of this matrix is 1. Also, the determinant of this matrix is 1. Now, why I start calculating with these determinants is, or excuse me, with these matrices is because these are some matrices that we've seen before. If you recall way back in chapter 2, these are the elementary matrices. So they correspond to the elementary row operations that we looked at in the previous chapter. So because these are elementary row operation matrices, they have special properties. In this case, I just want us to notice that the determinant of both of these is 1. Now there's other elementary row operation matrices as well. By the way, this is the elementary row operation matrix that is going to take row 1 of a matrix and -3 times row 3 of a matrix and replace it with, or excuse me, replace row 1 in the matrix with the sum of a row 1 plus -3 times row 3. This matrix would take and replace row 3 with 12 times row 1 plus row 3. So these are actually the row replacement operations. And you can also look at the other operations of elementary row operations. So one of the operations was multiply a row by a scalar. In this case, I chose 3. Notice that the determinant there is 3. Again, this is triangular, so you can just multiply the diagonals. So the determinant is 3 when I multiply a row by a scalar. Now this one, we could go through the calculations, do a column expansion. It turns out if you do a column expansion, it's pretty easy to do. You'll get since this is in the row 2, column 1 spot, so it's in the 2, 1 position, this one here, it's going to have a negative on it, and we'll have 0, -1, plus 0 times the submatrix. Well, the submatrix will just be the identity matrix. So basically, if you want to, you can do this by hand. Otherwise, you can just trust me that the determinant of the row swap matrix is -1. All right. So we have determinants of row replacement matrices or 1s, determinants of scalar times a row is whatever that scalar is, and the determinant of the row swap matrix is -1. Now also, it's pretty nice to observe the determinant of the identity matrix. Just observe that the determinant of the identity matrix is 1 as well. Now all of that, we've calculated these things. You could go through and see, oh yeah, any sort of row replacement matrix is going to have a determinant of 1. Any type of scalar multiple of a row is going to have a determinant of the scalar. Any row swap is going to be a -1 determinant. And so all of our elementary matrices have non-zero determinants. Okay, so there's none of those have 0 as the determinant. Now here's the really crucial property of determinants for this section. Okay, now we're going to leave the elementary matrices alone for a second. We're going to come back to those in a little bit, but this is going to be the really crucial property. If A and B are square matrices, obviously both have to be the same size for this to work, then the determinant of A times B is the determinant of A times the determinant of B. So while we know that A and B don't commute, the determinant function can in some sense distribute over multiplication. So determinant of A times B is the determinant of A times determinant of B. Now we're not going to prove that right now, but I do want to show you this property with an example. So if you would, I want you to do four things. Multiply A times B out, that's number one. Then find the determinant of A times B. Then find the determinant of A, then find the determinant of B. Okay, so I want you to find the determinant of the product and then the determinant of each one individually. Go ahead and push pause on the video and do that. All right, so hopefully you went ahead and did that. Now this one's pretty easy to do by hand. I'll show you just both the by hand way and the using the calculator as well. So let's start by doing this by hand. Okay, so we take our matrix 5, 6, 8, -2, and our matrix 2, 3, 0, 5, and we multiply. Now when we multiply, I'd go 5, 6, multiplied times 2, 0, so 5 times 2 plus 6 times 0 gives me 10. Then I'd go 5, 6 times 3, 5. So 5 times 3 is 15, 6 times 5 is 30, 15 plus 30 is 45, get that? 8 and -2, we're going to multiply times column 1 over here. So 8 times 2 is 16, -2 times 0 is 0, so 16 is the entry there. And then 8 times -2 times 8, -2 times 3, 5. 8 times 3 is 24, minus 2 times 5, which is 10. 24 minus 10 is 14. So it's a long, not real long to do, but not the easiest either. So there we go. So now determinant of A, 5 times -2 is going to be -10, minus the cross diagonal, 8 times 6, which is 48, obviously. So -10 minus 48 gives you -58. Now as far as B goes, 2 times 5 is 10, minus 0 times 3, which is 0. 10 minus 0 is 10. So determinant of B is 10. Now, if my property is correct, the determinant of the product of this should be -580. So let's calculate the determinant of the product. Take the determinant of A times B. Okay, so 10 times 14 is 140. 16 times 45 is 720. When I take 140 minus 720, sure enough, I get a -580. All right. Now, one of the interesting things that we're going to see is that A times B is this matrix, but remember B times A, like if I reverse the order here, B times A would not give me that matrix. In fact, B times A gives me something different. However, B times A will still have this negative 580 as a determinant because the determinant of each doesn't change. Negative 58 times 10 is the same thing as 10 times negative 58. All right. Now, if I were to do that on my calculator, I already have most of this stuff put in. So again, if you're trying to put things in your calculator, go into the matrix menu, edit. I already have A in as matrix that I was looking at. I already have my matrix B in as the matrix I was interested in. So if I want to go and find the determinant, I go to my matrix menu, scroll over to math, hit number 1 there, determinant. Oops. Matrix A. So determinant of matrix A is negative 58. If I go to the determinant of matrix B, that's a 10. And then I've already multiplied A times B. You could do this a number of ways, but you can check, you could find the determinant of A times B. Oops. I don't want that. Yeah, that's what I want. Sorry about that. So A times second matrix B. So I could put it in there and get negative 580. Or if you wanted to do it in the two-step process, you could multiply matrix A times matrix B, get that matrix. In fact, we can even store it if we want to. You can go down to this little store button here, STO, and you can say, well, let's store that as matrix C. So store that as matrix C, and then you could find the determinant of matrix C. And sure enough, any of the ways we do that, you're going to get the same results. So again, this isn't a proof that that multiplicative property has to be true, but this is a good example that shows the multiplicative property is true. So if we have the determinant of two matrices multiplied together, then we can take each of their determinants individually and then multiply up the determinants. Now, I do want to note that that property only works for multiplication. If you were to try to do that with addition, it would not work at all. We already found, so be very, very careful about this. Determinants do not distribute over addition, but determinants really work nicely with matrix multiplication. Okay? By the way, we've already calculated that this has determinant negative 58. This has determinant of 10. If you added these two matrices up, let's go ahead and do that. In other words, if you did A plus B, what you're going to get is a 2 by 2 matrix. And then obviously you just add each way pointwise. So 5 plus 2 is 7, 6 plus 3 is 9, 8 plus 0 is 8, -2 plus 5 is 3, and you're off to the races. So if you added up a plus b, you'd end up with 7, 9, 8, and 3. And so if you were going to find the determinant of a plus b, what you'd have to end up with is a 21 minus 72. All right, which has really no bearing on, whoops, I'm sorry, negative 51, which really has no bearing in relationship to my original determinants. Okay, so adding, you're not going to get nice properties, but multiplying matrices, you do get nice properties. So when you multiply two matrices, you can multiply the determinants individually. Adding, you cannot. Hopefully that all makes sense. All right, now let's connect this idea to invertible matrices. So we already saw that in section 2.2 that if A is an invertible matrix, then it's going to row reduce to the identity. So the row reduced echelon form of A is the identity. Now I should say that we are talking about square matrices here. So we were talking about 2 by 2 or 3 by 3 or 4 by 4 matrices. Okay, we're not talking about anything that has more rows than columns or more columns than rows. So number of rows and columns is equal in these matrices. So if you have a square matrix and it's invertible, then it row reduces to the identity. Now, row reducing to the identity means that you're going to have a bunch of elementary row operations applied to A, which gives you the identity matrix. Now, we can take a determinant of both sides of this equation. If you take a determinant of both sides, you take a determinant of a lot of products of matrices is equal to the determinant of the the identity. Now we already saw that when we calculated the determinant of the identity, that determinant was 1. We saw that in an earlier example. And we can break up this left-hand side into the determinant of the elementary matrices multiplied times the determinant of A. That's basically my rule, my multiplication rule we just went over. Okay? Now, here's what I said earlier. All of these elementary matrices have non-zero determinants. So when I take the determinant of all the products, the only thing it can't be is 0. So it's going to be a real number, and it is going to be non-zero. Therefore, whatever this real number turns out to be, I can divide both sides by it and find that the determinant of A is going to be 1 divided by some real number. Okay? And whatever number this is doesn't really matter. This could be 1/4 or this could be 400. But the point is, you can solve this equation for the determinant of A. And therefore, if A is invertible, the determinant of A is going to be a real number. And that real number is going to be non-zero. Okay? So this is what we get. We get that the determinant of the invertible matrix is not equal to 0. And if the determinant of the matrix is not equal to 0, the matrix will be invertible. All right, so it kind of works both ways. If A is invertible, then the determinant is not 0. And if the determinant is not 0, then A is invertible. Now, you probably would have guessed this, but if A has a determinant of 6, then the determinant of A inverse is the inverse of 6. So that would be 1 over 6. So that kind of showed up here. If you remember way back in chapter 2, we said, well, since this product of all of these matrices times A has to give me the identity, this product, whatever it happens to be, this product in here, is actually A inverse. So we can see that the determinant of A times the determinant of A inverse has to give me 1, so they have to be multiplicative inverses of each other. Again, if the determinant of A, for instance, is 4, the determinant of the inverse would be 1/4. If the determinant of A was 17, then the determinant of the inverse would be 1 over 17. If the determinant of A was -6, the determinant of the inverse would be -1 over 6. So again, multiplicative inverses, inverses of matrices have determinants which are multiplicative inverses, and that comes out of the fact that they have to multiply to give you the identity, and we know the identity has determinant of 1. So here's what we can do. We can use determinants to find out if matrices are invertible. So what I'd like you to do is push pause on the video, calculate the determinant of this matrix A, and then decide if this matrix A is invertible or not. All right, well, hopefully you went ahead and did that. Now this one would be pretty easy to expand on column 1. You get 4 times the determinant of this 2 by 2 matrix plus 0 times the determinant, or excuse me, minus 0 times the determinant of something plus 0 times the determinant of something. So if you wanted to, it'd be pretty straightforward to expand on this column 1. What I'm going to do is I'm going to utilize the calculator to do that. So what I have done is I've typed in matrix A into my calculator as A. So what I do there is go to the matrix menu, calculate my determinant of matrix A, hit enter, I got a -20. Now, what this means? Well, this means two things. First off, the determinant exists, and because the determinant exists, this matrix is invertible. All right, so A is invertible. Now, notice that the determinant can tell you if the matrix exists or not, or excuse me, if the matrix has an inverse, so if a matrix inverse exists or not, but it doesn't actually tell me what the matrix is. So in order to use that, we'd have to go back to our chapter 2 techniques. So we're not doing that right now, we're just using the determinant to see if a matrix is invertible. So A has a non-zero determinant, and therefore it's invertible. How about this one? All right, well, this one, again, I'm going to go back to my calculator and do this. No need to actually, I won't show you this, but I put this into my calculator. So I put this matrix into my calculator. I went to find the determinant, and the determinant was 0. And therefore, since the determinant is 0, this matrix does not have an inverse. So this matrix does not have an inverse because the determinant is 0. Therefore, A is a singular matrix. Again, remember that terminology from last chapter. Not having an inverse means it's singular, and now we know that that means that the determinant is 0. Now we can connect this to all of the stuff we talked about in previous chapters. We can mention things about linearly independent columns of A. We can talk about, do the columns span R3? All based off of the determinant. So this is the same matrix that we dealt with last time, or excuse me, on the previous example. In fact, it did have a determinant. Its determinant was -20. I say it had a determinant. Every matrix has a determinant. It had a non-zero determinant of -20. So the determinant was -20. That means it was invertible. That means it's going to row reduce to the identity. Now, if it row reduces to the identity, again, the identity is going to have a 1, 0, 0, 0, 1, 0, 0, 0, 1. And so this is what it looks like. So we row reduce the identity. That identity has ones at diagonal, zeros elsewhere. So are the columns linearly independent? Yes, they are, because we have no free variables. So you can't write one as a linear combination of the others. So yes. And do they span R3? Yes, because we have a pivot position in every row. Okay. Again, if you wanted to go back to section 2.3, that had all of our equivalent statements in it. And the fact that A is invertible already implied that the columns were linearly independent and the columns span R3. So since we know this A has a non-zero determinant, it is invertible, and so the columns are linearly independent. The columns span R3. We could go through all of those other statements too, but there you go. And by the way, with our other matrix here, are the columns linearly independent? Do they span R3? The answer is no to both. This will not row reduce to the identity because the determinant is 0. And so because the determinant is 0, it doesn't row reduce to the identity. A is not invertible. All these are equivalent statements. And so the columns are going to be linearly dependent, and the columns are not going to span R3. Now, the other thing we can do with determinants is we can use logic to ask ourselves, well, what are the determinants of, products of matrices, of those types of things, given that I don't know the matrix, but I know the determinant of the matrix. So let's take a look at this example. We have the determinant of A is 5, of B is 7, C is 10. So it says we want to find the determinant of the product of A and B, the product of B and A, and then the product of C, A, and B. So I want you to use the rule, the product rule on the determinant, the multiplication rule of determinants, to find those determinants. Go ahead and push pause on the video. All right, so hopefully you went ahead and did that. What I am going to do is I'm just going to do this there. So I don't even know how big A is, how big B is, how big C is. I am going to assume that they're all the same size so that the products make sense. So we're going to assume that they're all square and they're all the same size so that the products make sense. But other than that, I don't know what numbers are entered into A or anything like that. But what I do know is that the determinant works like this. If you take the product of A and B and calculate the determinants, the product multiplication rule of determinants says you can just take determinant of A, which is 5, multiply times determinant of B, which is 7, and I know that 35 is going to be the determinant of A times B. Now, if we did that with B times A, determinant of B times determinant of A, well, determinant of B is 7, A is 5, so again we get 35. All right, so A times B and B times A have to have the same determinant. Now this can be done over 3 matrices as well, or 4 matrices, or however many matrices we want. You could do determinant of C multiplied times the determinant of A multiplied times the determinant of B. All right, and when you take that, you go 10 times 5 times 7, you get 350. Okay, so there you go. So that's how we can use logic to find determinants of products of matrices. Now, by the way, this is just kind of an aside, but what would happen if I asked you to do the determinant of A plus B? Well, you'd say we don't have enough information. So, not that I would, but that is one thing that could come up. Probably won't come up in this class, but if somebody were to ask you, find determinant of A plus B, and you don't know what A is and you don't know what B is, you'd say not enough information. So there we go. But products work really, really nicely. So do inverses. So again, remember that rule about inverses. If the determinant of a matrix is 17, then its inverse has determinant, which is the multiplicative inverse, which is 1 over 17. So I want you to use that fact to solve these 3 problems. Find the determinant of B inverse, find the determinant of A inverse times C, and then find the determinant of C times A inverse times B. All right, so I'm going to solve that. Hopefully you push pause on the video. If you haven't, make sure you do. All right, so what I'm going to do is I'm going to say I want to find the determinant of B inverse. I know the determinant of B is 7, so the determinant of B inverse has to be the multiplicative inverse of that. So all I have to do is say, well, that's 1/7. Okay? Now, if we put the two properties of multiplication of matrices together, A inverse times C is going to have the same as the determinant of A inverse multiplied times the determinant of C, which, again, determinant of A inverse, A has determinant of 5, so A inverse has the determinant of 1/5. Well, C we know has a determinant of 10, so A inverse times C would have a determinant of 2. Very similarly, I won't go through all the steps, but if I do C, A inverse B, and I'm looking for the determinant, I'm going to take the determinant of C, which is 10, the determinant of A inverse, which we just found, that's going to be 1 over 5, and then we're going to multiply times the determinant of b, which is 7. Okay? So if I do c times a inverse times b, what we get, I believe, is a 14. So those are the answers to those 3 questions. Again, here we're just utilizing the inverse property that of determinants. Now, the observation that I've made already a couple of times, I just want to make that explicit. We know A times B is not the same thing as B times A in general. So we know matrix multiplication doesn't commute. However, because real number multiplication commutes, when you take the determinant of A times B, it will give you the same determinant as B times A. Okay? And by the way, the proof of that is just to say, well, determinant of A times the determinant of B has to be equal to the determinant of B times the determinant of A, because the real numbers, so they can swap spaces. But again, matrix multiplication is not commutative, but if we do have the same matrices being multiplied, no matter what order they are going to have the same determinants. Now, by the way, all of these, it was implied that B and A are square matrices which have the same size, okay? Otherwise, we're not going to calculate determinants for them. Now, the last thing is kind of just a mention here. So we've looked at a few rules of determinants. Of particular interest was the fact that non-zero determinants mean that my matrix is invertible. Zero determinants means my matrix is not invertible. And then the multiplication property. So those are the big 2, the invertibility and then the multiplication property. And as sort of a side note, I just want to mention that the book goes to show you that a matrix A and a matrix A transpose will always have the same determinant. Now this is pretty obvious because think about what you would do to find the determinant of matrix A. In the 2 by 2 case, you go AD minus BC. Well, if you switch the rows and columns, the A and the D stay put, but because this B is in the first row, it has to move into the first column. Because this C is in the second row, it's going to have to move into the second column. So we still get AD minus BC regardless. And the other, you can do this more in general too. If you think about row expansion on this first row, it has to be the same as the column expansion on the first column. So you're going to get the exact same matrices when you row expand versus when you column expand in the transpose. So transpose and A have the same determinant, and so it makes our life a little bit easier with determinants. Again, we're not going to use that property so much. The main 2 we're going to use are the fact that a square matrix is invertible if and only if the determinant is not 0, and the fact that you can multiply 2 matrices, take their determinant, and this resulting determinant is going to be a product of the 2 individual determinants. All right, those are the 2 biggies. Other than that, it's pretty straightforward. So hopefully we understand section 2 of chapter 3, and then we'll move on. All right, so this ends the section 2 of chapter 3.